Alright, Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh, and very good day to all students taking the subject of BMFG1213 Engineering Materials. So we shall continue the big chapter, functional properties of materials for chapter 6. And now we are going to discuss about magnetic properties of materials. Previously we have learned and we have studied about electrical properties of materials, including semiconducting as well as electrical conduction of materials. And for magnetic properties of materials, we will look into basic concepts of magnetic properties, diamagnetism, paramagnetism, and ferromagnetism, as well as anti-ferromagnetism and ferrimagnetism. So these are the learning objectives, right? Other than the magnetization of some materials, as well as the behaviors of the magnetic properties-based materials, we need to be able to describe magnetic hysteresis or BH curve, and the below part will be the third part for the optical properties of materials. And if you look into this figure for magnetic properties, we have a figure, an image of iron, single crystal iron photomicrographs, and magnetic domains change shape as the magnetic field H is applied to the right hand side, this one, and the domains favorably oriented with the field grow at the expense of the unfavorably oriented domains. So let's take a look on the origins of magnetic moments. It is a response to quantum mechanics laws. So the magnetic moment is not due to a current looped, but is instead an intrinsic property of the electron. We have two main contributions for that event to occur. Number one is for the orbiting electron or orbital magnetic moment, and B is the electron spin itself. So due to incomplete cancellation of electron spins and or orbital magnetic moments as a consequence of the electron structure. So look at this figure. We have magnetic moment A and B, in which we have atomic nucleus and surrounded by the electron, as well as the spin as an intrinsic property for the electron itself, and it is not due to its rotation. And the main concept is based on Bohr magnetron or Bohr magnetron. Most fundamental magnetic moments is equal to magnetic moment of electron spin. Mu b is plus minus 9.27 times 10 to the power of negative 24 ampere meter square. And the atomic moment is 2.22 for metallic iron, as an example. Basic concepts. Number one, magnetic forces are generated by moving electrically charged particles, and forces can be represented by imaginary lines grouped as fields according to the right hand rule. Okay, hukum tangan kanan. And we know that material has magnetic dipoles, north or south, utara atau selatan, magnetic field lines of force around the current wire loop, and a bar magnet on the right hand side. The left hand side is the wire loop, and it is represented by red arrowed line. That is the magnetic field lines. Magnetic dipoles can be found in magnetic materials. It can be thought as small bar composed of north and south poles. It is influenced by magnetic field and tend to orient themselves with field. Itu konsep yang dalam kompas dan sebagainya. For the vectors, externally applied magnetic field is equal to magnetic field strength H, and if H is generated by a cylindrical coil solenoid consisting N closely spaced turns. So this is the equation. Magnetic field strength is equal to H equal to Ni divided to L, whereby L is the length in meter and I is the applied current. And unit will be amperes per meter or ampere turns per meter. Magnetic induction is equivalent to magnetic flux density, or B, represents the internal. Later we will look into the relation between B, magnetic flux density, and magnetic field strength. So magnetic flux density, or B, represents the internal field strength within a substance subjected to a magnetic field. The unit is Teslas, T, or Webers per square meter, WB stroke M2. And this is the example of iron bar magnetized by H. And then we have B there as magnetic flux density is equal to, without iron bar, B prime or BO is equal to mu O H, and with iron bar, the equation will be B equal to mu H, and magnetization of solid can be Xm times H, whereby M is proportional to the applied magnetic field H, and Xm is the constant or magnetic susceptibility as per shown in the equation below. This one. We know that mu is permeability, mu 0 is vacuum permeability around 4 pi times 10 to the power of negative 7 Tesla meter per ampere, and unit for magnetic flux density will be Weber per ampere meter, or Tesla meter per ampere, or Henrys per meter. Sometimes they use Henrys. H. Basically, H is from the concept of magnetic properties, Henrys. So we have magnetic induction by solenoid, macam yang ada dalam with the bar ataupun without iron bar, as well as magnetic induction by magnetized iron bar, and you will get the equation of mu H. Now let's focus on the diamagnetism and paramagnetism. So what is diamagnetic material? It is a very weak form of magnetism. Very weak form of magnetism can be found in all materials. It is non-permanent, persists only with applied external field. In these materials, all electrons are paired, so no net magnetic moment per atom. In the presence of a field, the alignment of magnetic path occurs. Dipoles are induced and aligned opposite to the field direction. Magnitude of induced moment is extremely small. Mu r is slightly less than unity, in which in this case magnetic susceptibility is negative, in the order of minus negative to the power of negative 5. And B, the magnetic or field strength is less than in vacuum. Example of diamagnetic material will be copper, silver, and gold. Whereby paramagnetic material is for material that the atom has permanent dipole moment, which is uncancelled electron spin and orbital magnetic moments. The representative will be magnesium, molybdenum, lithium, and tantalum. In paramagnetic material, in the absence of H, random moments orientation with no magnetization, and in the presence of a field, atomic dipoles preferentially aligned by rotation with H, and dipoles acted individually with no mutual interaction. So both materials are non-magnetic, exhibit magnetization only with the presence of H, and B is almost the same as it would be in vacuum. Of course, we know that atoms are easily moving, can move easily in vacuum condition. The concept you need to understand. That's why microscopy, by using electron movement concept, is being used in high vacuum condition, for example. Okay, electron beam deposition, for example, in vacuum or high vacuum condition. The flux density B versus the magnetic field strength H for diamagnetic and paramagnetic materials. So we have vacuum condition, we have paramagnetic on the top of the vacuum condition, and diamagnetic on the above side. Okay, ini kita dah tengok tadi lah, magnetic flux density. So looking at the room temperature magnetic susceptibilities for diamagnetic and paramagnetic materials as shown in this table. Examples of diamagnetics are aluminum oxide, copper, gold, silicon, silver, zinc, and the susceptibility or Xm values there with SI units. And we have paramagnetics, aluminum, chromium, sodium, titanium, zirconium, right, with the values of susceptibilities, magnetic susceptibilities or Xm. Next, we move to ferromagnetism. In certain metallic materials, we can find permanent magnetic moments and mutual alignment of atomic dipoles with the absence during the absence of H. It results from uncancelled electron spin and orbital magnetic moments. Coupling interaction between the atoms forces magnetic moments of adjacent atoms to align with one another. This is called magnetic spin. Coupling forces arises from the electronic structure of coupling forces may arise from the electronic structure of the metal. In it manifests very large and permanent magnetization M. Example of the materials are iron with BCC ferrite, you dah belajar. BCC body centered cubic, ferrite, we know ferrite has a lot of crystal structures. Cobalt, nickel, gadolinium. So basically they are transition metals in the middle of the periodic table, kalau you faham. And then these are the domains or the crystal regions of mutual spin alignment for ferromagnetism. Maximum magnetization or saturation magnetization MS is equal to all magnetic dipoles in solid mutually aligned with H correspond to saturation flux density B, and the equation of MS is equal to M atom times N atoms. What are M atom? Different material could be different. For example, Fe is 2.22, Co, cobalt is 1.72, and nickel is 0.60 respectively. Rho in this equation, an atom can be, of course, density of atom, and then Na is Avogadro number, and A is the mole per atomic weight. So you need to understand the Bs, the flux density, should be mu S times Ms. Ms is M atom times N atoms, and the number of atoms, N atoms, is equal to the equation we discussed just now. But above the Curie temperature, Tc, it will become, or all the materials become paramagnetic instead of ferromagnetic, instead of having the consistency in being a ferromagnetism. So it will become paramagnetic above the Curie temperature. What is Curie temperature? It is the temperature at which certain materials of ferromagnetics lose their permanent magnetic properties to be replaced by induced magnetism. Anti-ferromagnetism should be the vice versa of ferromagnetism, experienced by materials that are not ferromagnetic. Okay, for example, manganese oxide. When a magnetic field applied to this kind of material, alignment of the spin moments of neighboring atoms or ions in exactly opposite directions. So no net magnetic moment, or for O2 minus ions, total cancellation of both spin and orbital moment. But for M and O manganese oxide, Mn2 plus possesses a net magnetic moment, or moments of adjacent ions are anti-parallel. Opposing magnetic moments cancel one another, so no net magnetic moment. Nothing happened for the magnetic properties. Example, in 1986, superconductivity discovered in layered compound lanthanum, barium, copper oxide with a transition T much higher than expected. Little was known about copper oxides, so they explore about these kind of materials, saying that copper oxide, for example, planes exhibit anti-ferromagnetic order. This work initiated the continuing exploration of magnetic excitations in copper oxides of superconductors. Okay, crucial to the mechanism of high temperature superconductivity. Alright, so we move on to ferrimagnetism. Some ceramics, one of the engineering material, exhibit permanent magnetization termed ferrimagnetism. It is different with ferromagnetism in the source of net magnetic moments, exhibits by some ceramics which are permanent magnet in nature. And then principles is actually can be illustrated by cubic ferrites, macam dalam gambar ni, cubic ferrites. And the chemical formula is MFE2O4. M is for any metallic elements. For example, in Fe3O4, what is Fe3O4? What is the scientific name? Right? So it is a magnetite. Fe3O4 is a magnetite. Fe or iron. Ions exist in both +2 and +3 ions. We know about that. And it has a different spin magnetic moment configuration. Exists as anti-parallel spin coupling interactions. So we know that sometimes it can be ferromagnetism, sometimes can be ferrimagnetism, and sometimes can be anti-ferromagnetism. Depends on the condition of the matching metal or metallic elements, or as well as the temperature behavior or temperature condition for any experimental condition. So application for this kind of ferrimagnetism material is for non-volatile memory drives such as hard drives. So ferromagnetism requires free electrons in the conduction band. Kita dah belajar electrical conduction of materials, and then we have ferri and anti-ferromagnetism can also occur in insulators. So it covers metals and metal oxides. These are the distribution of spin magnetic moments for Fe2 plus and Fe3 plus ions in a unit cell of Fe3O4. Of course, we need to say that in Fe3O4, the Fe2 plus and Fe3 plus are present, and then it can be octahedral latticide, tetrahedral latticide, as well as net magnetic moment. Fe3 plus will be complete cancellation here for net magnetic moment. And then each arrow represents the magnetic moment orientation for one of the cations, right? So this is the picture again. The blue one is the O2 minus, the orange one is Fe2 plus, Fe3 plus is the green one, and Fe3 plus with tetrahedral condition or crystal structure will be the yellow one. So net spin magnetic moment or Bohr magnetons is as per listed in the table here. Okay, so I'll move to the next one. These are the XM values or magnetic susceptibility of all elements presented in periodic table. So all values given for a temperature of 300 K, which is room temperature condition. In case of ferromagnetic material saturation, we call them saturation polarization. So the blue part is the diamagnetic area. Paramagnetics is the light gray one, and the dark gray will be the ferromagnetic. It's quite it is producing quite good magnetic properties. So it has been used as in many examples of applications for electronic devices, for example, transistor, capacitor, as well as other catalytic. So it will contribute to catalyst performance of the material to be used as catalyst in growing carbon nanotube, for example, from catalytic chemical vapor deposition process, and they are also being used in as a catalyst in growing so-called two-dimensional nanomaterials like graphene, right, MXene, and so on. So let's take a look on the influence of temperature on magnetic behavior. So we know that raising temperature will increase magnitude of thermal vibrations. That is number one. By that, atomic magnetic moments will be free to rotate. So that increased T tend to randomize the directions of moment that may be aligned. In ferro, could be ferri or anti-ferro, atomic thermal motions counteract the coupling forces, cause misalignment of the motions, for example. So results in decreases saturation magnetization MS. So MS will decrease. So MS is equal to 0 at Tc, which is Curie temperature, and Tn we know as a nil temperature for antiferromagnetic. So Tc is good for ferromagnetic and ferrimagnetic. So this is the behavior for pure iron and so-called good magnetic material Fe3O4 magnetite Fe3O4. So this is the behavior of the iron-based material for if you look into the influence of temperature on the magnetic behavior. And then for ferro and ferrimagnetism, to summarize, at 0 Kelvin, thermal energy of material is 0, the saturation magnetization will be at maximum, and the hysteresis loop will have the largest area. We'll take a look on hysteresis after this. At a higher temperature, yet below the Curie temperature, the saturation magnetization will decrease and the size of the hysteresis loop will diminish or eliminated. Finally, above the Curie temperature Tc, ferromagnetic behavior ceases and the material becomes paramagnetic with linear B versus H behavior. Kita akan tengok lepas ni B versus H, and the slope of this line segment is very gentle, right? 0 Kelvin, just below Tc, above Tc. B versus H. B versus H. So what is B versus H, right? B is in y-axis, and H magnetic field strength on the x-axis. In ferromagnets and ferrimagnets, B is not directly proportional with H, not directly proportional. But if ferro and ferrimagnetic materials initially unmagnetized, it will start at origin of BH curve here, 0.8.0. Slope of BH curve and origin is equal to mu I, which is equal to initial permeability. As H increases to the right hand side, B slowly increases, then rapidly and finally leveling off, becoming independent of H. Maximum B is the MS as it reaches saturation and magnetization. Domain change configurations, shape and size during several stages of magnetization due to the movement of domain boundaries. Initially, domains are random, oriented in direction favorable to applied field, and expand of those are unfavorable. And it will stop at saturation point when all domains align with H field at saturation flux density BS here, saturation level. Okay, so what is hysteresis? So we know that ferromagnetic material subjected to forward and reverse saturation. Okay, basically hysteresis is going up like this. Dia akan patah balik, going remove the reversal of the same line at the same axis of x and y. So when H field is reduced by reversal of field direction, B field lags behind the H, decreases at lower rate. So, and then we can see the remanence flux density exists of residual flux density materials remain magnetized without H when H is 0. Due to resistance to movement of domain walls and H is equal to 0, some net fraction of domains in forward direction to reduce the B is equal to 0, H field of magnitude HC must be applied in opposite direction called coercivity or coercive force. Coercivity or coercive force. This is the one of the main important element in if you want to understand about the spintronic device, for example, so-called the magnetic material related study, electric or ferromagnetic materials related application, for example. And continuing applying H at this direction achieves saturation at S prime. Okay. Second reversal to the point S, mula dia pergi sampai S, kemudian reverse. To complete the symmetrical hysteresis loop, yield negative remanence minus BR and positive coercivity HC. So basically the term is symmetrical hysteresis loop. So it is the flux density versus field strength H, and hysteresis loop is in the red one with initial magnetization at the blue point, and remanence is BR. BR is the remanence, HC is the coercive force or coercivity. Okay, so we have plus negative C and plus C, we have plus BR and negative BR. So that is the concepts of hysteresis. Alright, comparison of between magnetic versus non-magnetic. Okay, I will say that ferromagnetic and ferri is the magnetic, and the diamagnetic and paramagnetic is the non-magnetic. So B versus H, kalau ferromagnetic and ferrimagnetic, it will give a good sign of curve. And for diamagnetic and paramagnetic, it's going to be directly proportional between B and H. So no curve at all. So let's take a look on soft and hard magnetic materials. The main important concept is that the hysteresis loop, the loop magnetic energy loss per volume of material per magnetization or demagnetization. We can see energy loss there manifested as heat generated within this magnetic specimen by increasing the temperature. Both ferro and ferrimagnetic materials are classified as either soft or hard. It can be soft or hard on the basis of their hysteresis characteristics, size and shape. So kalau dia kecil, if it is small, the hysteresis is small, it's going to be soft magnetic materials, and if it is big, based on size and shape of the hysteresis loop, is going to be hard magnetic materials. Right? One familiar example consists of transformer cores, for example. It is the characteristics should be thin and narrow and must have a high initial permeability and a low coercivity. Maknanya H tu negative and plus H is quite small value. That is could be the soft one. This is the schematic for magnetization curves for soft and hard magnetic materials. Magnetic materials are utilized in permanent magnets, which must have a high resistance to demagnetization. In terms of the hysteresis behavior, a hard magnetic material has a high remanence, high coercivity, and high saturation flux density, as well as low initial permeability and high hysteresis energy losses. Two most important characteristics related to applications for these materials are called coercivity or coercive force, and what is termed by the energy product, and what is termed the energy product or stored energy in magnet designated as BH max. B for flux density, H is field strength. The value of the energy product is a representative of the energy required to demagnetize a permanent magnet. The larger, the harder is the material in terms of its magnetic characteristic. Hard magnetic materials fall into two main categories, conventional and high energy. For conventional, of course, they need to have BH max values that range between about 2 and 80 kilojoule per meter cube, 0.25 and 10 megagauss or stats, MGOE. These include ferromagnetic materials, okay, macam cakap tadi, transition metal, for example, magnet steels, CuNife alloys, AlNiCO alloys, as well as the hexagonal ferrites. Ada barium kat sini, BaO, barium oxide, combined with ferrites ataupun iron oxide. For high energy hard magnetic materials, the energy products in excess of about 80 kilojoule per mole. Okay, not just now is between 2 and 80. For the case of high energy hard magnetic materials, it should be exceeding or accessing 80 kilojoule per meter cube, and it is considered to be the high energy type. These are recently developed intermetallic compounds that have a variety of compositions. The two that have found commercially available or commercial exploitation are samarium cobalt SmCO5 magnets and neodymium iron boron Nd2Fe14b magnets. Okay, so that's all, guys, for part 2. This is the end of part 2. I hope you will understand a little bit more or less on the contents of the magnetic properties of materials. So next we will move to the last part, which will be the optical properties of materials. Thank you and have a nice day.